So we're going to talk a little bit more about Gauss's law here. Gauss's law says the net flux through any surface is equal to the integral around a closed surface. If you want, we can put surface there, but it's really what that little loop means. E dot n hat dA is equal to Q enclosed over epsilon naught. So this is an integral of the dot product of the electric field and the normal vector to the surface over the whole surface. And so if there's an equal amount of the electric field going into the surface and out of the surface, this thing will integrate to zero. And so what it's really saying is the net flux only occurs when you have something inside the surface, so that the net electric field is either leaving if it's a net positive or coming in if it's a net negative. And so, I can draw a surface like this, and I can say this is Q1, and I can say over here is Q2, and this is a 3D surface, and I can say Q1 is equal to minus 2 microcoulombs, and Q2 is equal to 1 microcoulomb, and then I can say what is the net flux through the surface. And so we're going to evaluate this, right? And all we need to do that is to evaluate this, right? And so the enclosed charge, enclosed, is equal to minus 2 microcoulombs plus 1 microcoulomb, which is minus 1 microcoulombs. And that's equal to minus 10 to the minus 6 coulombs. That's my enclosed charge. And so that means the net flux is minus 10 to the minus 6 coulombs over epsilon naught, which is 8.85 times 10 to the minus 12th. And so if you evaluate this thing, it's coulomb squared over Newton meter squared. That's the units on the bottom guy. And this comes out to 1.13 times 10 to the minus 5th Newton meter squared per coulomb, and that's Newton per coulomb times meter squared, which makes sense because it's an electric field, which is Newton per coulomb times an area, and that's what this thing is that you're integrating with a minus sign. And so if you're just calculating the flux on something, it's often easiest just to take these two pieces of the equation. Usually we're only grabbing this part of Gauss's law when we're evaluating an electric field. Right? That's what that one's for, most of the time. And so I can give you a few other things about the flux. We can say, for example, a charge Q is at the center of a cube. What is the flux through one side of the cube due to the charge? And so here's my picture, right? I have a cube. There we go. Right, and I've got right in the center, I've got a charge Q, right? And so the overall flux is just Q enclosed over epsilon naught, which is just Q over epsilon naught, right? But this is a cube, and we don't just know the flux through one side. Well, since the charge is in the center, the flux through each side is the same, and so phi through one side, again, due to the charge, is Q over 6 epsilon naught, because the flux is divided evenly among the 6 sides of the cube. if you put the charge in a corner, right, so that only a quarter, so imagine you did it this way. Leave the charge in the center, right? And now divide the cube into 8 boxes. So here's a, so we do lines all the way across. We split every side in half, right? How many more of these do I have to draw? There's one there, there's one there, there's one there, there's one there. Something like that. Does that get all of them? I think I don't have that one. And I don't have that one there. And now everybody's, there's 1, 2, 3, 4, and then in the back 5, 6, 7, 8 boxes. Right, I think that one has to go across there somehow. And so this charge here is divided with 1/8 of the charge in each box. And so each box, there's the center line, each box gets 1/8 of the flux. Each full box gets 1/8 of the flux. And so if you look at just one box, let's pick the box out on this corner. I'll redraw it over here. Right, it looks like that. There we go, right? And now the charge is down in this corner, except most of the charge is, if it's a sphere, is not in this box, but it's outside the box, it's in the other box. It's only 1/8 of the charge because it's split among 8 boxes. It's in this box. And notice that if we let the limit of it get very small, that none of the flux goes through this side or the back side or the bottom side because they're along the line of the flow, like the electric field here would be flowing parallel to this surface, and so it wouldn't be going through it. Same thing with the bottom surface. And so all of the electric field comes through the front surface, this box, and this box, and this box. Those 3 sides get all of the flux from a charge that's in the opposite corner. None of the flow goes through the sides that are adjacent to this, to where the charge is. And so I don't know what I really mean by opposite sides, but the 3 sides that aren't the adjacent sides, right? How about share? So if the charge at the center of this guy is Q, that means the charge in the corner of this box is 1/8 Q, and each one of these opposite sides gets 1/3 of that, so each one of these opposite sides gets 1/24 Q. Sorry, Q over epsilon naught for flux. So that's just a few little things about flux. The flux, you don't have to worry about the electric field integral. You're just worrying about the enclosed charge and which surfaces are available to it. So in this problem, we're going to use Gauss's law to figure out what is the electric field inside and outside of an infinitely long solid cylinder of radius r with charge density rho. So there's charge throughout this. It's solid. And we want to know first what the electric field is outside of the cylinder, and so we're going to draw a little. Hopefully you can figure out how to draw a Gaussian surface for this by now. The Gaussian surface is going to be a cylinder, right? Hopefully of radius little r, right, which is larger than big R, right? And there's our top piece. This is the point that we're interested in. Right, this guy goes around like that, maybe, I don't know, like that, right, connects over here somehow, All right, I didn't do that very well. How about if I do it like that and draw that like that? And this is a cylinder. Probably that line should be dotted, maybe, because it's inside. It's behind. Or it should go like that. All right. Anyway, you get the idea, right? So we want to use Gauss's law, which is the net flux equals the integral around a closed surface of E dot n hat dA, and that's equal to Q enclosed over epsilon naught. And so we're going to be using this piece now because we're going to evaluate the electric field. And hopefully you can look at this picture and say, well, the electric field, sorry, I see now. I'll just leave it. It should be like this. But anyway, the electric field is radial, right? And so it's pointing outward all the time, all the way around the sphere. So it points up here, it points out, and it points down on this side, right? And because of the geometry we've chosen, this exactly will match the normal to the surface, right? Both the electric field and n hat will point in the same direction, so that dot product just becomes a times 1. Again, n hat is a unit vector, and so that's on the curved part. Notice on the flat part, the normal vector points perpendicular to the flat part, right? But the electric field still points radially because this black cylinder is infinite. And so the electric field is always pointing outward. And so on the flat part, E dot n hat is 0. And so if I write this, I'll drop off the flux since we're not evaluating. I can say, look, this integral becomes the integral over the curved part of E dot n hat dA plus the integral over the ends of E dot n hat dA is equal to Q enclosed over epsilon naught. And again, on the ends, n hat points this way, and the electric field points this way, and so this guy is just 0. And so that leaves me with the electric field over the curved part. By symmetry, first of all, they always point in the same direction, so that's just E times dA, right? Because the electric field and the normal vector always point in the same direction as the same part on the curved surface. And by symmetry, the fact that at every point on the red cylinder, its position looks the same as any other point on the red cylinder because it's just above another cylinder by the same distance. The electric field has to be constant over this curved surface, and so what we get here is E times the integral of dA over the curved part is Q enclosed over epsilon naught. Well, the integral over the curved part is just the area of the curved part. That's just 2 pi r times the length, right? And so if we say that our Gaussian surface has a length L, then we can say, look, this says that E times 2 pi r L is equal to Q enclosed over epsilon naught. But the charge enclosed is just the density times the volume that's enclosed by my red cylinder over epsilon naught. The volume that's enclosed by the red cylinder is pi big R squared times L. Right? So the charge that's enclosed is just whatever charge is in the black cylinder, the solid cylinder, that's inside the Gaussian surface. And so the Gaussian surface is length L, so if you just chop off that much of the black cylinder, that gets you, and determine how much charge is in there, that's the Q enclosed. And the charge that's in there is just the charge density times the volume of material in the black cylinder. And so the volume of the cylinder is is pi r squared times the length. And so divide that by epsilon naught, and we get E is equal to, so you ready? It's rho r squared L over 2 pi r epsilon naught. If I had a pi in here, there's a pi in there. And so the pi's go away, and it's equal to rho r squared L over 2 epsilon naught r. The L's cancel. Sorry, I lost an L. There was an L here and an L here. The L's cancel. There we go. That looks better. So you'll notice, actually, that this is the exact same result we got in the last series from a wire that had a linear charge density of lambda. And I can sort of show you that because we can calculate the linear charge density for this guy, right? We said that in this length, Q is equal to the Q enclosed is charge density times the volume, which is rho times pi r squared times L. And so lambda is the linear charge density, and that's just Q divided by the length. And so that's equal to rho pi r squared. Well, this says that rho r squared is equal to lambda over pi, right? If I divide this side, if I set this side equal to this side and just forget this for a second, then I divide by pi, I get rho r squared is equal to lambda over pi, and so I can replace rho r squared equals lambda over pi, and this becomes lambda over 2 pi epsilon naught r. And if you go back and look, this is the formula we got for the electric field due to a wire. So they're exactly the same. And it's what we expect, because when you're outside that charged surface, the electric field is just a radially symmetric outward going electric field due to either the solid cylinder or the wire. It looks exactly the same once you're outside it, if you're just looking at the electric field where you are. And so we expect those two to agree, and they do. Now we need to look inside, and so I'll just erase this diagram and redraw it, kind of thing. And so now we're going to be inside the wire, or excuse me, inside the cylinder. And so I'll draw the cylinder bigger this time, right? And so I'm saying, look, this is the outside and this is the outside, so I'm going to dash that part. Hopefully you can figure out what I'm doing, right? And this is my cylinder, right? And then here's the center. And now I'm going to draw a Gaussian surface. What do I do with my red one? Maybe it's here. Maybe it's here. Ha! So I'm going to draw a Gaussian surface, and this time I'm looking at r less than r, where this dude here is r. And so I want to draw a smaller cylinder. I'll just draw it inside. Right. There's my cylinder there. This has length L. This is radius r, little r, right? And so once again, if I want to know the electric field, I can make all the same statements. The electric field out here is going to be outward. I'm just looking at what's happening due to the stuff inside for now, and it's going to match up with the normal vector to my they're all going to point in the same direction. The electric field and the normal vector for my Gaussian surface are going to point in the same direction. The Q enclosed, that's awkward. The Q enclosed is just like it was before. It's the density times the volume, but this time It's the red volume. It's the volume that's contained inside. Both times it was the volume that's contained inside my Gaussian surface, but before it was the volume of this thing, because the solid cylinder was carrying the charge, and my Gaussian surface was larger, and so I just needed to accumulate the charge inside the solid cylinder. Here now, my Gaussian surface is smaller, and so I have to take the smaller volume, which is this becomes the density times the volume of this cylinder, which is pi little r squared times the length. And so this is my enclosed charge. Now if I write Gauss's law, I can say phi net is equal to the integral. So we're going to integrate over this part, but I'm going to break it up into the curved part of the cylinder, which is E dot n hat times dA, plus the integral over the ends of E dot n hat dA is equal to Q enclosed over epsilon naught, or rho pi r squared L over epsilon naught. And so just like before, we can say, look, the normal vector points to the outward on the sides, but the electric field still points radially. And so these two guys are perpendicular, E and n hat, on the ends, and so they contribute nothing. And so if I just take these two pieces, I get the integral over the curved part of E times dA. I don't have to worry about the dot product anymore because the electric field and the unit vector point in the same direction. So the integral of the curved part of E dot dA is equal to rho pi r cubed r squared L over epsilon naught. This is equal to, if I integrate this, it gives us E times the integral of dA over the curved part is equal to rho pi r squared L over epsilon naught. The integral over the curved part is just the curved surface area of the cylinder. We've done that already. That's this becomes E times 2 pi r L is equal to rho pi r squared L over epsilon naught. The L's cancel, the pi's cancel, 1 r cancels, and we get the electric field is equal to rho r over 2 epsilon naught. And this is a little bit smaller than what it was for a sphere, right? For a sphere inside the solid sphere, it was rho r over 3 epsilon naught. A couple of things to notice. One is that if you look at what happens when r equals r, you'll get the same result you got in the previous problem where we were doing outside the sphere. So they agree at the edge of this, outside the cylinder. So they agree at the edge of the cylinder. So for r less than r and r greater than r, the functional forms of those agree at little r equals big R, and that's good. So it's continuous. The other thing is that at little r equals 0, in other words, right at the center, the electric field is 0 because rho times 0 is 0. And that's good because you wouldn't expect there to be any preferred electric field direction in the center. It would have to be 0 at the center. And so, so just like inside the sphere, it increases linearly till you get to the edge of the sphere, and then it falls off. This one falls off as 1 over r. Outside the sphere, it falls off as 1 over r squared. A couple of things, just a few other things about Gauss's law. You can say some interesting things about what happens inside a charged surface. So So if I have some surface right here, right, and it's charged, say, positive on the outside, and we want to know what the electric field is inside, we can draw a Gaussian surface on the inside, right? And all Gauss's law tells us is that the net flux through this surface is 0. It doesn't tell us that the electric field is 0. It just tells us that the net flux through the surface is 0. So, for example, suppose I have suppose I have some charges over here, right? Let's separate these drawings. So I've got some plus charges over here and some minus charges over here, and I draw some Gaussian surface in between them, right? Well, the net flux through this surface is 0. But that just means that the electric fields which run across here, right, every electric field line that goes in on this side goes out on this side, and so the net flux is 0. It doesn't say the electric field is 0 everywhere. But you can use Gauss's law to show that in symmetry cases like this, that the electric field has to be 0 everywhere inside the sphere. And so I'll show you that by doing this. We, once again, like we do with Gauss's law many times, is we take advantage of the symmetry of this picture, right? Let's assume for the moment that the electric field due to these guys is stronger than that due to the rest of these guys. And so there's a net electric field in this direction at this edge of the sphere, because it's closer to these guys than it is from those guys. Again, we're assuming this is a symmetric picture, so the charges are smoothly distributed around here, right? Well, if that's true, then it's also true over here, and then it's also true over here, and then it's also true over here, and then it's also true over here. It has to be true everywhere because it's a symmetric picture, right? And so if these guys are more influential than these guys, then the electric field points in everywhere on the sphere. But that would mean that there's a net flux into the sphere because it's not pointing out anywhere. And that's not possible unless there's a charge inside. And so the only way for you to have a symmetric picture here for the electric field around this Gaussian surface is for the electric field to be equal to 0. And of course I can draw this sphere as any size I want. I can draw it right up to the edge, right? And the electric field has to be 0 inside it and on the surface of it. Any sphere I draw is going to have an electric field of 0 on its surface, and so that means the electric field has to be 0 anywhere inside a spherical charge, a spherically symmetric charge distribution. I'm probably not saying this well, but what I mean is you have a spherically symmetric charge distribution, and inside a hole in that, the electric field is 0 everywhere in there.